Hello students, in this video we will discuss the solution to the questions 1 through 5 from exercises of chapter number 2. So let's start. Question number 1. Which of the following binary operations are closed? So for this one, let us consider the A, subtraction of positive integers. Of course this is not, because if we take any two integers, suppose we are taking 2 and 3 and we are subtracting them, then we are getting negative 1, and this is not a positive integer, not positive integer, and therefore this is incorrect. Second one, division of non-zero integers. So when we divide any two integers, suppose 1 and 2. So after division, in terms of binary operation, we can write something like this: 1 and it operated with 2, and for this one we can write 1 by 2 right away. And therefore it is not necessary an integer, because this is fraction number and this is what we say, this is a rational number, and not all rational numbers are integers. So this is also not. Number C, function composition of polynomial with real coefficient. So let us see this. Suppose we are taking some polynomial px, and this is equals to a0 plus a1x plus a2 x square, for example, and then another polynomial qx equals to b0 b1x plus b2 x square. So this is, we are taking, for example, a2 is non-zero and b2 is non-zero, and of course all ai and bi are real numbers, as we need to take function composition of polynomials with real coefficients. So let us consider P of Qx, composition of these two. So how we can write with the definition of this one? So we can write a0 plus a1, and in place of x we need to write Qx. So Qx is what? b0 plus b1x plus b2 x square, and plus a2 b0 plus b1x plus b2 x square, the whole square. And when we simplify this, so what we get? a0, and from here a1 b0 plus a1 b1x plus b2 x square plus a2, and we need to expand this one. So b0 square plus b1 square x square plus b2 square plus x to the power 4, plus other terms are also there, plus 2 b0 b1 x plus 2 b1 b2 x cube plus 2 b0 b2 x square. So when we simplify this, what we get? a0 plus a1 plus b0. This is a constant term, and let us collect coefficient of x. So what we have? a1 b1, and then from here we can get another coefficient. So 2 times of b0 and b1, plus similarly we can collect a coefficient of x square, and then x cube, and then x to the power 4. So what we see, because all ai and bi are real numbers, so their product also real number and their sum also real number. So all coefficients will be real, and therefore function composition of polynomial with real coefficient is closed under the operation. So this is correct. Multiplication of 2 by 2 matrices with integer entries. So we can consider, let us see. suppose we are taking any 2 by 2 matrix A equals to A, B, C and D, and then another matrix B, E, F, G and H. When we multiply these two, so how what we get from here? A, B, C and D, E, F, G, H. So multiplication is row into column wise. So we start from here and then here. So A, E plus B and G. Similarly, other terms we can also write. So let us observe here. So they are the product of two integers, A into E. Both are integers. So therefore, product is also integer. B into G, this is also integer, and sum is also integer. So similarly, other three entries will also be integer. Therefore, all entries of A times B are integers, and therefore the operation is closed. So this is also correct. What about exponentiation of integer? About exponentiation, let us take suppose we are taking some integer. Suppose for equals to n equals to, we are taking 3, and then we are raising an exponentiation -2. So they are not saying that just a positive exponentiation or something like this. So we can take -2. So 1 upon 3 square. So 1 upon 9. So this is not an integer. Not integer. And therefore this is incorrect. So therefore only two correct, C and D. So let us move to next question. Question number 2. Which of the following binary operations are associative? So certainly, if we talk about subtraction, this is subtraction of integer. In fact, this is not an binary operation, because just we have seen in the last example, if you take 2 minus 3, so what we are getting? We are getting -1, and this is of course a negative integer. Of course, it is negative integers. And then if we take all positive integers, here the subtraction of positive integer was here. So this was not because this was not positive integer, therefore it was not closed. So this was incorrect. But in this question, what we have seen, subtraction of integer. So of course, when he subtracts two integer, then we get another integer, whether it is positive, negative or 0. So of course this is not the another case what we have taken in the question number 1. So let us see. Let us take some example. 1 minus 2 and minus 3, something like this. Then we can take, if this is equals to 1 and minus, then 2 minus 3, something like this. Then let us see whether does it hold or not. So 1 minus 2, so -1 minus 3. In the left side, what is right side? 1 minus, and here we get, if we simplify this bracket, -1. So what we get? 1 plus 1. So this is equals to 2, and here -4. So of course they are not equal. So this is not correct. Division of non-zero rationals. Division of non-zero rationals. So when we divide rationals, non-zero rationals, suppose A by B, one rational is there, and then we are dividing it by another rational, suppose C by D, so it becomes D by C, and then E by F. So we are taking here 3, A by B, C by D, and E by F. So let us start. A by B divided by C by D, and then it is divided by E by F. And this we need to check whether A this is equals to A by B divided by C by D minus E by F. Of course, we can verify that this is they are not equal. So this is just a matter of simple calculation. You can verify. So this is also not correct. Function composition of polynomial with real coefficient. As previous, we can verify it. Just we have seen in the last example, last question number 2. So this is correct. Multiplication of 2 by 2 matrices with integer entries. Just we have seen that multiplication of 2 matrices with integer entries are closed under multiplication. So of course it is well known that multiplication is always associative of matrices. So this is also correct. And exponentiation of integers. So this is not correct. You can see. Just we have taken one example in the last question. So similarly, we can take another example and we can show that it does not hold in general. So let us see next question. Question number 3. Which of the following binary operations are commutative? Subtraction of integer. So same example we can take whether they are commutative or not. So 2 minus 3 equals to negative 1, and this is not equals to 3 minus 2. So this is not commutative. Division of real numbers. Of course, all we know that AB is not always equals to B by A. So this is also equality may not hold. Unless both A and B are same, that is 1 and 1, or that is A equals to B. Only this case this may hold, otherwise not hold. So function composition of polynomial with real coefficients. So of course we can take the same example and we can see P of Qx is not equals to Q of Px. Px. So same example we can take. So we can take Px equals to a0 plus a1x plus a2x square, and then Qx equals to b0 plus b1x plus b2x square. So let us find here Q of Px. In the last question number 1 we have derived when P of Qx. We have found the expression for this one. Here let us find this one. So when we put this is b0 and b1 at place of x, a0 plus a1x plus a2x square, and plus here we can write b2 of a0 plus a1x plus a2x square. So let us compare. The constant term is b0 plus b1 and a0 is there, and plus some coefficient of x, coefficient of x square. So let us compare this thing only. So what we see here, we have constant term b0, b1 into a0. So in the question number 1, then we have derived this one. So what we got, a0 a1 plus b0, a0 a1 plus b0. So this was at that place a0 a1 into b0. So of course certainly they are different. So means in general P of Qx is not equals to Q of Px. So let us see the next problem. Which of the following sets are closed under the given operation? Addition modulo 16. The set is given A equals to 0, 4, 8 and 12. So we need to use addition modulo 16. So 0 plus 0 many times, how many times we add, it will be here 0 only, and 0 plus 4 is 0, 0 plus 8 is 8, 0 plus 12 is 12, so 0 plus 4, 0 plus 8, 0 plus 8, 0, 0 plus 8, and 0 plus 12. Of course, 0 plus 0 is 0, and this is 4, this is 8, and this is 12. So all belongs to this set only, A. And again, if we add 4 plus 4, that is 8, member of that set only. So similarly, 4 plus 12, that is equals to 16, and 16 is nothing but when divided by 16 gives the remainder 0. So similarly, we can 12 plus 8, we can find out it. This is 20, and 20 divided by 16, it will give us 4. Or we can make a table, table plus 16, here 0, 4, 8 and 12, 0, 4, 8 and 12. So here 0, add 4, 8, 12. So this also 0, so 4, this is 4, 4, 8 and 12. So 4, 4, 8, this is 12, and this is 4 plus 12, 16, that is 0 then. So 8 and 4, 12, 12 and 10 divide, only 12, this is, and 8, 8, 16, 0, and this is 20, 20 then 4, divided by 16. So 12 into 4, so 12 plus 4, 16, 16 when divided by 16 gives 0 remainder. So 12 plus 8, 20, 20 divided by 16 gives 4 as remainder. So we see in each row and each columns are elements of A only. So this is closed under the given operation. The second question, similarly we can verify 0 plus 4 is 0, and 0 plus 8 is 8, 0 plus 12 is, so with 0 there is no problem. 4 into 4 plus 8, so 12, no problem, 12 is there. 12 in 12 plus 8, 20, 10 divided by 15, what we see, 8 plus 12 under 15, so this gives 20, 20 divided by 15 gives 5, but this does not belong to this set. Suppose this set is B, so this does not belong to B, so this is not. So let us see C1, the question C part 1, 4, 7 and 13. One, 4, 7 and 13, and operation is multiplication modulo 15. Multiplication modulo 15. It is better to make a Gallian table and then we can decide everything. So multiplication modulo 15, 1, 4, 7 and 13. 1, 4, 7 and 13. 1, 4, 7, 13, 1, 4, 1, 4. This is 7 and this is 13. Of course, 4 into 4, 16, and when divided by 15, remainder is 1. 4 into 7, 28. 28 divided by 15, 13, and here we will get 7, of course. So similarly, 7 into 4, 28. 28 divided by this one, 15, it will get 13. So 7 into 7, 49, and 49 divided by 15, so this will give us 4. So what remains here? 7 into 13, 51, and then remainder is 1. No, 91. So it is 1. So similarly, here also we can write 13. We can fill 13, 52, 52, and then 15. 52 divided by 15, so 49, so 3 here, 13, this is 45 and then 7. So we will get 7 here, and then 13, 91 when divided by 13 we get 1, and then here 7. So all we get all elements belongs to the set C. So this is also correct. This question is also correct, and this is also closed. Similarly, D. In case of D, what we see, multiplication modulo 9. So in this case, if we take suppose 1 into 4, 4, 1 into 5, this is 5, 1 into 7, 7, 4 into 5, so 20 divided by 9. So when 20 divided by 9, so remainder is 2. But 2 is not there. 2 is not there. So therefore, this is not closed under multiplication modulo 9. So this is also not closed. So 2 is closed. A and C, these are right. So let us take next question. Each of the following case, find the inverse of the element under the given operation. So what is there? When we write Z20 means we are talking about the operation under addition. So 0, 1, 2, 3, up to how many numbers up to 20 is there, so 90, up to 90. So under addition modulo 20 we are talking about. So they are talking about the inverse of 13. So additive inverse of 13, the number we need to find, which we add here and divide by 20, gives the remainder 0. 0 is nothing but additive identity. So 7 is there. So inverse of 13 is 7. And now in question number 5, B part, U14. So let us take U14. What are the elements are there? 1, 2 is not there. All those integers, positive integers, which are less than 14 and relatively prime to 14. So 1, 2 not there, 3 is there, and then 5 is there, and 6 cannot be there, and 7 not be there, 8 cannot be there, and 9 may be there, and then what about 10? 10 cannot be there, and then 11, and then 12 cannot be there, 30. So these are the elements of 14. So what is the question is that what is the inverse of this one? In fact, when we talk about UN, the two elements 1, 2, up to n minus 1, when we form this set. So n1 and n minus 1 is always self-inverse. So 13 into 13. 13 into 13 multiply and just divide by 14. You will get the remainder 1. As all we know here, 13 into 13, this will give us 169, and then divide by 14. So 14 when we divide by 14, it will give us remainder 1. So 13 is self-inverse. Then similarly here also, so this is general case of this question. So what we can see, n minus 1. Now I claim that n minus 1 is self-inverse. here also. So n minus 1 into n minus 1. This will give us n minus 1 whole square. This is equals to n square plus 1 minus 2n, and this is equals to n, and when you get n minus 2 plus 1. So of course when we divide it by n, the remainder is what? Remainder will be 1. So similar the case here also. So when we multiply these two and when we divide by 14, the remainder will be 1. 169 divided by 14. Remainder will be. So here the answer is 7, here 13, here n minus 1. Now next question, 3 minus 2i in complex number. So let us see. For this one, we can refer the example number 14 of your book. So for the complex number with non-zero complex number, inverse of this type of element a plus bi is given by this. So just put here a equals to 3, b equals to negative 2, a equals to 3 and b equals to negative 2. So 3 minus 2i inverse of this one. This equals to 1 upon, so just square and then add. So 9 plus 4, 13, and a is what? 3, and minus 1 upon 13, and b is negative 2, and then I. So this is equals to 3 upon 13 minus plus 2 upon 13 I. So this is the answer of D part of question number 5. With this, I finished today, and then let us meet in another video. So the remaining question I will be discussing over there. Thank you very much.